All right, let me get your attention, please. Quiet. All right, you guys haven't said hi to Cole in a while. If you want to say hi to Cole, you can. All right, that's it. He is in Tornado Land, isn't he? Nebraska, so. Quiet, please. Oklahoma, Iowa. I think Nebraska a little bit. Maybe not as bad as some of these others. Alabama, stuff like that. Okay, we got to get going. 12.3b. Classifying quadrilaterals by the number of sides. And really, this should simply be the aspect classifying quadrilaterals. And remember, a quadrilateral is really 4 sides. Again, you guys, first edition and notes. And so really 4 sides. Classifying quadrilaterals. Remember, any quadrilateral has 4 sides. And there are a lot of different ones. And that's what we're going to talk about. So, again, classifying quadrilaterals, I'm talking about 4-sided figures here. All right, first one. And let's see if you know the name. So don't say it out loud. But does anybody know the name of that shape? Either one, they're both the same. They are quadrilateral. No doubt about it. They have 4 sides. Andrew? Not a rhombus. Nick? They are trapezoids. T-R-A-P-E-Z-O-I-D. Trapezoid. T-R-A-P-E-Z-O-I-D. It is important that you learn how to identify your shapes. It is important that you learn how to name them. And that is a trapezoid. How do you recognize them? Well, you got to know what a trapezoid is. It's a quadrilateral, meaning it has 4 sides, with at least one pair of parallel sides. So take your red of your red pen and go over this side and make it look red if you can. And then go on the bottom side and make it look red if you can. If this were a second edition of notes, I'd have them read for you already. Do you see how those lines look parallel? And they are. There's the one pair of parallel sides. The figure to the right is also a trapezoid because this line here is parallel to this line there. Do you see the parallel lines? Again, I would draw over your lines in red to try to illustrate the pair of parallel lines. Technically, a quadrilateral has at least one pair of parallel sides, though normally we just think of the objects that only have one pair of parallel sides. Again, it's got to have 4 sides, and one of the pairs are parallel. Jordan. No, there is no way this line is parallel to that line. Because if they keep going, they are going to intersect. And maybe we have enough room to even see it. Sure, there we go. Parallel lines have to be the exact same distance apart. And if they keep going, they'll never, ever, ever cross. The red ones will never cross. If I drew them perfectly straight, they'd never cross ever, ever, never, 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 never. All right? So a trapezoid. You've got to be able to recognize trapezoids. Later on, we're going to learn a formula for area of a trapezoid. And that formula is unique to only a trapezoid. So you've got to recognize, how do you do an area problem for a trapezoid? First, you got to recognize, oh, it's a trapezoid. And then use the formula. So, got to know your shapes. So, if you haven't learned them yet, learn your shapes. All right, what's next? Don't say it yet. Oh, I did use my color here. This is a quadrilateral with, take your blue, 2 pairs of parallel sides. So, that's the condition. Now we have a quadrilateral 4-sided figure with 2 pairs of parallel sides. And that is called Connor. No, sir. It is not. Pamela. It is a parallelogram. I love that word. P-A-R-A-L-L-E-L-O-G-R-A-M. Parallelogram. That's a tongue twister. Minus 20 points if you spell it wrong, of course. Parallelogram. Learn how to spell it. Quadrilateral with two pairs of parallel sides. And you can see by the color on your illustrations, the red sides are parallel and the blue sides are parallel. Hence, we don't have a trapezoid anymore. Technically, we do, but we're not worried about it. Technically, every parallelogram is a trapezoid, technically. But more specifically, we get to call it a parallelogram, because only a parallelogram is a parallelogram. All right? So it's got to be quadrilateral, four sides. Both sides have to be parallel, and that's a parallelogram. And it's going to have its area formula as well. All right, number one. Here we have a shape with four right angles. I'm sorry, with four right angles. Yes, all right, that's good. The markings, first editions. We'll fix it up here in a minute. Okay, so let's go ahead and put right angle symbol there, right angle symbol there, right angle symbol there, right angle symbol there. And we got to fix the markings. And let me go. This should be a 2 marking, and this side should be a 2 marking. All right, there we go. Now it's what we want it to be. All right, we have a parallelogram. Don't the top and bottom look parallel, and don't the left and right look parallel? Surely they do, and they are. And so we have a parallelogram with, but this parallelogram has, the opposite sides are also congruent, right? And we all know the name of this is a rectangle. Nothing strange there, rectangle. Is that this? Are you doing this? That's this, not that. That. All right, so everybody knows a rectangle. Now we've got another parallelogram. So what do we call a parallelogram with 4 congruent sides? Don't say it out loud. Both shapes are this, the one on the left and the one on the right. So whatever you say has to fit both shapes. Not just the left shape or not just the right shape. They are both this. And Kaylin, these are Kaylin, these shapes are a rhombus, of course. Very good. So what was question 21? Anybody remember it? Is every square a rhombus? No. All right, quiet. Let me read it. Quiet. Shh. A rhombus and a square are the same thing. Here's a square and here's a rhombus. Are they exactly the same thing? No. They're both a rhombus, but they are different rhombuses, aren't they? Yeah, they're not the same. So, and that's why the answer was no. Now, I don't know if that even helps you, Kaylin, but you can see, even though a square is a rhombus, not every rhombus is a square. And that's why they're different. Okay? In our square, all 4 angles are congruent, aren't they? Are all 4 angles of the other rhombus congruent? No, let's use our markings. This angle is congruent to that angle. If you had a protractor and you measured the angle, they'd be the same. However, this angle is different, so I'm giving it a 2 marking. But it is congruent to the angle opposite it, which is up here. So opposite angles of any rhombus are congruent. If you get to a square, all four are congruent, right? So again, I'm going to mark my right angles in on my square. Okay? Any questions on our shapes? So let me recap real quickly. Trapezoid, 4 sides, 1 pair of parallel sides. Parallelogram, 4 sides, both opposite sides are parallel. A rectangle is a special parallelogram with 4 right angles. Let me ask you this. Is a square technically a rectangle? Isn't it a parallelogram with 4 right angles? It is. A square is a parallelogram. A square is also a rectangle. And a square is also a rhombus. That square gets around a lot. All right, it fits a lot of categories. And so know also what a rhombus is, a parallelogram with 4 congruent sides. All right, next page. Next page. Here comes the math of this section. Finding the number of degrees of the interior. Finding the number of degrees of the interior angles of a polygon. All right, there's a formula for this. And I've got the full formula for you. The only thing we have to figure out is what in the world n is. All right? You might wonder what d is. D is the number of degrees. All right? That's what we're solving for, right? D is the number of degrees. Anybody have any idea what n would be? N? Ileana? It is the number of sides. Remember, polygons are classified by the number of sides, right? Let's do a real quick review. Shout out the answer if you know it. 4-sided. Quadrilateral. 7-sided. Heptagon. 9-sided. Nonagon. 12-sided. 12-sided. Dodecagon. Right? The other ones you should know by just common sense: 3 triangle, 5 pentagon, 6 hexagon, 8 octagon, 10 decagon. All right, be careful. Again, as I admonished you in the beginning of the chapter, you should be reading through your notes. It doesn't take long. Just read through them. If you do it once a day, this stuff will stick a whole lot better for you, and you won't get confused, and you won't forget stuff you need to know. Okay, so n is the number of sides. N is the number of sides. Now, don't do this on your paper. I want to show you why the formula works first, though you don't need to write it. All right, we have an example here of how many sides. Let's see, don't do this. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so here we have a heptagon, a 7-sided figure. Now, if I wanted to break it up into triangles, do not do this on your paper, and get the, without anything intersecting, how many triangles will I end up with? So remember, this is a 7-sided figure. Watch how many triangles I have. 1, 2, 3, 4, 5. Look at the formula. What's 7 minus 2? 5. How many degrees are in each triangle? 180. That's where the formula comes from. We're trying to figure out the total sum of all the degrees. And every polygon, the number of triangles, the least amount of triangles you get, which will allow you to figure out the angles, is always the number of sides minus 2. Then 180 degrees for each triangle, and that'll get all the degrees of all the interior angles. All right, if you understand that or not, it doesn't really matter. Just the fact that you can use the formula is all you really need. So when we look at a problem like B, it says find the sum of the interior angles of the heptagon. We don't even really need a picture. When we see the word heptagon, we know we have 7 sides, right? So I'm going to write the formula once just to begin to help me to remember it. And every problem you guys have today, I want you to write the formula for each problem. What am I trying to get you to do is learn the formula, right? And besides, that's what we're subbing into. Now look, there's only one place to put a number, right? It's n. So it's pretty easy. This is a heptagon. By the way, you got to know a heptagon is 7, because normally I'm not going to give you the picture. We're just going to say heptagon, or we're going to say dodecagon, or we're going to say, quadrilateral, or we're going to say decagon. So again, that's why you got to know your shapes. Okay, that's really about all the work we need. We can simplify right there. And we're going to take our calculator. We're going to multiply 5 times 180, right? Grab your calculator, 5 times 180. Somebody raise your hand and let me know when you got it. Jack, what do you got? 900 degrees, right? You want to include your degree symbol. That's the work I'd expect to see on your homework in a problem like that, right? Not a lot there, trying to get you to learn the formula. Kirsten. You should include the degree symbol. Again, it's because you know what you're talking about. Just like if you have feet or millimeters, include the symbol there for degrees. It helps to explain what's there. Okay, let's see. See if you can do C. Here, I'll give you a big hint. D equals parentheses n minus 2, close parentheses, times 180. There you go. Big hint for you. Go ahead and solve C. All right, you don't even need your calculator to do this one. Piece of cake. 10 times 180, 1,800 degrees. Of course, you used a comma, right? Whenever you go into the thousands. Any questions on that? It's not hard, right? That's pretty easy. Nothing terrible there. All right, well, let's get to a horse of a little bit different color. Now, the key to the last thing we're going to do today is number 3 in the blank. Because this is only for a certain kind of polygon. And if you misappropriate the formula, it's not going to work. What does misappropriate mean? Use it in a wrong way, right? When a person misappropriates funds, they take money that's supposed to be used for one thing and usually use it for themselves, right? Misappropriation of funds. Hey, don't misappropriate the formula. You can only use it in what it's designed for. So this is designed for finding the number of degrees of an angle. Now we want the number of degrees of the angle, not all the interior angles together, but the angle of a, and before I finish, let me go back to my heptagon here, and let me show you what happened on our heptagon. Just want to be clear. I'm going to use a number. You can do this on yours. I'm going to call this angle 1, and I'll call that angle 2, and I'll call that angle 3, angle 4, angle 5. Again, you can do this angle 6, angle 7. Just want to make sure you understand what we found. What we found is measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 plus the measure of angle 4 plus the measure of angle 5 plus the measure of angle 6 plus the measure of angle 7. Good thing I didn't do a isosagon. Equals 900 degrees. That's what we found. So if I were to take a protractor, matter of fact, I have a minute here, so let me take my protractor. Come on, protractor. Spazzing out. Look, the pen thing. Doesn't know what to do. Let me make sure. All right, let's see. Come on, give me the protractor. Oh, I guess I just had to click it. All right, operator error, mine. All right, here's the protractor. Well, I better shrink it, huh? Can anybody still see it? Who's got good eyes? Okay, you can come up to the board. Come on up to the board, somebody with good eyes, and you want to try to read this angle for me. Well, yeah, but her glasses might make it... Not yet, hold on. Her glasses might make it to where she can see it more clearly. Still not. Yeah, it's okay. According to this protractor, how many degrees do you think it reads? Again, we're reading this ray and this ray right here. Looks to be about, yep, going around. So that's 110, 120, close to 130. All right. I think it's maybe 120. I don't know. Let's take 130. Take your calculator, multiply 130 times 7. 130 times 7. What do you get? 910. All right, so it's actually, this is a weird one. It's actually not an exact number. This is really 129 point something. Do 129 times 7. We're probably still a little bit big, right? Okay, because look, actually, I can see I'm a little less than 130. So this is really like 128 point something. Every one of those 7 angles to total up to 900. Do you follow now what we found? We found all of them added up. Okay, let's go back now to where we're at. So we can find the number of degrees of each of those angles for a regular polygon. So let me show you what this formula is. See if it'll do it. Okay, I didn't think it would. Let me not include the D here. Whoa, it's undoing all my stuff. Okay, get it back. We'll get there. We'll get there. Okay, what does that look like? What equation? What does that equation give us? No, what does it give us? The total degrees, right? Correct? Doesn't that part give us the total degrees? So what's the bottom? And what is n? The number of sides. So let's go back up to this one. How many angles were in this polygon? No. How many angles? 7. Divide 900 by 7. And we'll find out exactly how many degrees each of these angles are. Say it when you got it. So round off to one decimal place, 128 point. Now we know the number of degrees of each angle. And you know what? Quiet now. No matter how big the heptagon, no matter how small the heptagon, if it's a regular heptagon, and that's what I used. By the way, the first formula will figure out the degrees of any polygon, regular or not. The second formula is only for a regular one, and we'll find out exactly how many degrees each angle is for the regular one. So the first formula will work on any kind of polygon, regular or not. But if you want to find the individual angle, you can only find it for regular polygons. All right, so that's the formula. Pretty easy to use. I'll just leave that circle there. Let's do a couple quick problems. Find the measure of the interior angles of a regular polygon. Okay. We're going to use our formula. D, number of degrees. N minus 2 times 180 over N. Just takes a second. Helps me to remember the formula. All right, let's put in N. We have a pentagon. So that's 5 minus 2 times 180. And what do I divide by, class? 5, the number of sides. All right, go ahead and punch it out. See if you can get it on your calculator. You all know 5 minus 2 is 3. So you got 3 times 180 divided by 5. 108 degrees. Quiet, please. So if I had the time, I would again measure this with my protractor. But this is 108 degrees. This is 108 degrees. This is 108. This is 108. And this is 108 because it's a regular pentagon. Hey, if you wanted to, go to the Pentagon and measure their angles of the building I'm talking about. They'd be 108. It'd be a cool field trip. How many of you have been to the Pentagon before? It's like a museum. Only that few? Too bad you guys already had a field trip. All right. That would be a cool field trip. I might be able to swing it. Who can get us into the Pentagon? Who's dad? Anybody's dad work at the Pentagon? Well, Secret Service, so you have connections everywhere. Anybody's dad work at the Pentagon? Did. Nobody's still there? All right.
I can call one of my friends.
All right. Anyhow. Okay. I want you to do the last one. Quiet, please. Last problem. Finish it up. Find the measure of an interior angle of a regular octagon. Octagon. Here, I'll give you the hints. There you go. Now you need a hint. Done already, Caitlin? Hold on there. Just takes a minute to show the work. That's all I need for the work. In class, the answer is... Shh. No matter how big that octagon is, no matter how small that octagon is, if it's regular, every one of its angles are 135 degrees. No matter how little, no matter how big. It's 130. Take a stop sign, take your protractor up to a stop sign, and measure the angle. It'll be 135 degrees. It will. All right, here's your homework. To the next time we meet, page 506, 23 to 32. Remember, if there's a pick to draw, draw the pick. 38, 45, and the ever popular 47.